Our final talk in the morning session will be by Jordi Barro from the University de Barcelona on quasistatic kinetic avalanches and SOC in deviatorically loaded granular media.
Hello, everyone. First of all, let me thank the organizers of this talk for their hospitality, receiving me here, and especially because I got the opportunity to meet personally, let's say, and put faces to the authors of so many papers that I've been reading during my career, right? And until now, I couldn't have the opportunity to meet you. So thank you very much. So I'm going to present today's work that was published a few years ago with this title, Quasistatic Kinetic Avalanches and Self-Organized Criticality in Deviatorically Loaded Granular Media. It was published in PRL in 2021. It is a work that started as a collaboration between two groups in the University of Calgary at that time. It had a group, it was the group by Jörn Davidson, where I was working in complex systems, and the group by Richard Won and Mehdi Puraga that was on civil engineering, right? So it was an interdisciplinary work. The point I finished this working on Barcelona when I was back in Barcelona. That's why I'm acknowledging as well the financial support there by AXA Research Fund. And now that both Mehdi Puraga and me were postdocs at that time, now we are more on tenure track positions, and we had the opportunity to secure some funding thanks to the NSERC and the Spanish Ministry of Science and University to follow this research. That's what I am retaking this, right? I added this subtitle, Upscaling Dynamics from Isostaticity to Soft Matters, just to put into the context, right, of this upscaling in complex systems. That is the topic of this FRAC meeting of 2022. Just to begin, I will give a summary. First, I will start talking about these problems of upscaling, this idea of the stability in what we talk with fragile matter or granular matter. Then I will talk about the simulations that we used, DM, so discrete element models, right, to define these kinetic avalanches and to identify these avalanche phenomena. On the third part, I will talk about one specific result, that is we found this criticality in a kind of a stable evolution state that I will explain in a moment what it is. And for part, I will go to the global aspects and talk about how we found this non-universality of exponents that I will found here in the part 3. Okay. So first of all, let's talk about this upscaling in complex systems in a general way, let's say, especially in this problem of stability in fragile matter, right? So this is a work by Cornelius Escher. You're probably familiar. It's called Metamorphosis, and I think it illustrates pretty well what happens in complex systems, right? So we start in a system that we understand and we see, we understand well what is happening here. These are some birds, but as soon as these birds start to interact together, right, we get these murmurations, we get these nonlinear behaviors, right, in general in complex systems that mutates, let's say, the system in something that it's hard to be recognized, right? So essentially, we have problems to find ways to explain or to model this kind of phenomena. But if we scale it up enough, sometimes, I mean, our mind has this miracle, let's say, that is able to recognize patterns everywhere, right? And this is this quotation by Whitner that you have here in this school, right? That how we are able to use mathematics to be able to recognize new laws, let's say, and new descriptions at a higher scale, right? That probably has nothing to do with the description that we had at lower scale, right? This was an idea that was introduced especially by Phil Anderson more than half a century ago, right? And it was the basis of his critique to the constructionist reductionism. So in his work, he said that the ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws, let's say it's birth, right, and reconstruct the universe, right? That's why we usually approach from an empiricist point of view, same problem at different scales with different representations, right? And this is a little bit what happens when we talk about this fragile matter problem, right? So from a static equilibrium point of view, if we have hard spheres, let's say, and we want to put them together in a box that they maintain equilibrium, static equilibrium, this is a purely geometrical problem, right? So it can be solved with this Maxwell construct, right? Stating that the number of constraints has to have certain a certain relation with the number of particles and the dimension, right? On the other hand, when we talk with large system of particles, especially when this is soft matter problem, right, that we identify this static situation as this idea of the jamming transition, right, that we are able to represent in terms of thermal noise, of, for example, this deviatoric stress and the porosity of the system or the density of the system, right? We identify this surface here, this kind of manifold that contain this jam state situation, right? And in between, that's a problem, right? We have a void between these two extreme representations that we try to fit, and in fact, much clever persons, authors, I mean, like Edwards, Blumenfeld, and Ball, okay, they try to find this kind of parameters that are able to reproduce or to explain how granular matter behaves in terms of like a thermodynamical system, right? So this is the underlying problem, is how to upscale between this hard space description and the soft matter description, the thermodynamical scale, right? And this is something that is non-trivial. I mean, this is how Randall Munro described it after talking with Karen Daniels, right? That this is like describing sun is like one of the hardest problems that you can have in physics, right? In general, complex systems, right, are very hard to explain. So this is something that I try to stay away for it, but it was the matter of concern of this person here, of Mehdi Porral, who at the time was a postdoc in Calgary in civil engineering department, right? And now he's a professor in the university. Now he's a professor at the University of Carleton University, in Ottawa, right? So he had this engineering formation, so he's an expert, especially on these stability problems in complex environments, right? And he come to an idea. I try to summarize it here, but I'm not the expert on that. But the idea is the following. I mean, imagine that you start with a granular system that is on a static equilibrium, right? And you start to compress it uniaxially, right? Now consider that you have two different configurations here. One is loose assembly, so it's below, let's say, the stability, the stable density, and the one is above, right? So this is dense. This is just a 30% difference between one and the other on the density of the particles, right? So this is over-densified, and you see that the over-densified case, you have first strengthening, and then you have this force weakening regime, right? And then on the loose assembly, the particle just keeps pushing one against each other until you get the same stationary regime, right? So from a mechanical perspective, you have like two different paths that brings to the same stationary regime. This is also non-monotonous transition, right? And this is something that, of course, just looking at the stress strain, we will be unable to reproduce this kind of behavior, right? He realizes that if we look at it with from a different perspective, looking at the geometry of the contact forces here, at the contact between particles, you can see a different picture, right? And it's that from the loose assembly, you simply start with low coordination number. That means the particles are loosely connected, and then they start to grow a little bit to this limit, while this fibrec anisotropy is increasing. This is just the anisotropy of the direction of the contact force, right? So we are going towards a regime where the contact seems to be organized in a certain direction. Right? On the contrary, in the dense part, we start at high coordination number, and then we lose this contact very fast. In fact, this is this line here that is losing contacts by increasing as well this fibrec anisotropy until we get this tip here of anisotropy, and then it goes back, right? So essentially, this final point here seems to lie inside a kind of a limit surface here. And if we add here the rigidity ratio, he found out that you can build this manifold that is very similar to this idea of jamming, but that it works well in these intermediate scales, right, of granular matter, right? And in fact, by performing different kind of mechanical tests, he observed that they all seem to evolve towards this final state, this final we call this a stable evolution surface, or a stable evolution state. Right? So how this is the idea he had in mind when he realized that we were a group working on complexity science. He addressed us, and we tried to study this. He had different problems that what I'm going to talk about, but initially, I mean, the first thing I observed was this. Of course, these fluctuations there at this final state, right? Because I was working on avalanche dynamics, and this is something that is not common in engineering. In engineering, I mean, it's very easy to disregard this as noise, a simple noise, but in physics we know that this is something different, and this could be the underlying 1 over f noise, right? That simply, if you look at the spectral density of this noise, we may identify power law relations, power spectrum, let's say, and this happens at different scales. This is observed for very simple systems like interconductivity of vacuum tubes or superconductors, to the pulsation, let's say, or the rates of the noise on the heartbeats, or even in a single neurons in the brain, in the activity of the brain, right? Again, in magnetoencephalograms and electroencephalograms, and also in decision making, for even on the noise, underlying noise of compositions and the cognition of human for the human condition, right? In general, we develop, during the 80s, the authors developed 2 different explanations to that I would say they are complementary, depending on the systems. One is this is the outcome of adaptation, the other that is the outcome of self-organization. So essentially, this is the idea of developed by the people on Santa Cruz, right? That adaptive complex systems, which is just systems that are really, really complex, that are able to self-organize themselves into a way that they can survive in difficult environments. So what we'll say, let's say, an intelligent system, right, tend to organize towards this regime, what they call the edge of chaos, that is where fluctuations seems to progress not indefinitely, but they don't explode exponentially, which you would expect in a chaotic system, and don't die fast, right? So you identify here as something related to complexity, criticality in terms of statistical physics. And in parallel, we had this idea by Perbac, right, of self-organized criticality. Says that identified that even simple systems like a pile of sand or a pile of rice, this is the Oslo experiment, can exhibit this transition towards this critical behavior, this ping noise. So this distribution of noise like this that we can explain in terms of avalanche dynamics, right? So essentially, here when we usually talk about a spontaneous system, here we talk about externally driven system, and I mean, here we usually consider continuous signals. Now we can study this in these systems as punctuated or intermittent events. That is what we call the avalanches, right? And just allow me this little joke. If this is the root, let's say, of intelligence is in adaptation, let's say, and self-organized criticality is like the seat of these adaptations, right? I would say that the group on Oslo could be the parents of artificial intelligence, right? And somehow. But I guess this is more on the philosophical side. Okay, so going back to the data, so what we do is to perform these simulations much slower. These are discrete element model simulations, and you see that this noise then is more spiky. I mean, you see that this is shorter in time. This is a way I will trademark of the presence of avalanches. Let me play a movie here. So this is a little bit what I'm showing there. So this is the deviatoric stress. You see that whenever we have this noise, we see a drop in the deviatoric stress, right? So it seems to accommodate the stress more equitatively, right? And at the same time, we see an increase in the kinetic energy inside the particles of the system. So here I'm showing the actual sample. This in gray, these are the grains are difficult to see. The important thing maybe here is these black lines here. These are the force chains, right? This is how the force is structured through the contact points and distributed. And you can see that during the avalanches is changing, right? There's the amount of stress that are supporting this change is changing. And then the color, this is the kinetic energy of the particles that it's just coarse grain, but you can see that. And that's the interesting part, that the kinetic energy can start, so particles can start moving in some place, but then rapidly move to other places and can go all around the sample. And this is important for what I'm going to explain later. In any case, I will have this running. Tim.
Well, right, stall for two.
They change, I mean, especially change in this case, probably there is no buttering, no clear slide. Let's say the particles are small, right? And they just transfer a little bit of stress, let's say, right? I mean, you don't see here, I wouldn't say that there is, well, maybe just some forces are breaking. This means that we have some contacts, losing some contacts during the avalanche, right? But very small one, not the large ones.
Okay, thanks.
Yeah, sorry, this is our with friction. And I will explain that just in a moment. It's with friction and elastic particles, right? Yeah, okay. Okay, so this gives the idea that indeed we have avalanches here, right? And we are going to want to find some way to characterize them. Okay, so first of all, to see if really we are detecting avalanches here. And there's an interesting question that we couldn't address, but we would like to address at some point, is if whether we can define the states from this idea of SES instead of the traditional jamming representation. And what we are going to address here is how these avalanche statistics are in this SES, and what we can talk about the system and the nature of this stability limit, right? So this is the second part, is on the simulations details, right? So essentially I will focus on how we identify these avalanches during this quasi-static biaxial compression of compact granular assemblies. So we'll do this the following. It's the same experiment as before. So we compressed vertically at a constant rate, a constant strain rate, controlling the strain, and then we confine this as a constant pressure, right, on the lateral bonds, right? But what we add here is to add this quasi-static condition. So first of all, we drive the system very slowly, so there is very little inertia to the system. And when we observe that there is a jam in the kinetic energy, we stop the driving, right? This is represented here. We stop the driving, then when it goes above a certain threshold that is defined by the expected affine deformation or affine deformation, the kinetic energy here. And then when it goes above, then we stop the driving, and then we resume it when we believe that all the energy is dissipated already, right? This is a method that was developed by Mark Robbins several years ago. Okay. So what we will do is to play with the parameters. So basically, we control 4 different parameters. One of them is the size of the sample. The number of particles will be quite trivial. It's just a scaling relation with the results, right? Here is the initial porosity. This is what defines whether we are in a dense or loose assembly, let's say at the beginning. Surprisingly, it looks like the statistics doesn't change much depending on the initial porosity. Once we hit this SES, it looks like everything the statistics are the same. The driving rate has no effect at all, just on the limit to detect avalanches. So this implies that we are indeed in this quasi-static regime where we don't see inertial effects. And the most important aspect here will be the confining pressure, right? So how much pressure we impose by the lateral bonds. And this has a direct relation with the rigidity of the particles. The higher the confining pressure, the lower the rigidity, the softer the particles are, right? And this is what will have a most relevant effect on the statistics. That's okay. So now what do we do? First of all is to look at the energy balance. So we want to understand these avalanches from internal measurements of the sample, not from the external ones, because we may miss something on the external measurements. And then we see what happens here, that we are inputting energy through work by external driving, right? And this is dissipated. Well, first of all, this increases the strain, so the elastic energy on the contacts, and overall sometimes we have this release of kinetic energy that then is fast dissipated, right, by viscous drags that is proportional to the velocity and frictional forces, right? And also, this is important, we have to add here the presence of this work that goes to the lateral walls, right? So essentially, what happens is that since we are not considering any heat, this is a thermal condition, so the work that we apply finally is only transferred to the lateral works or transforming the internal elastic energy, right? Now what we do is to define these avalanches when we detect the jumps on kinetic energy, because we want to describe it in this way as a point process. So we have an intensity of these point processes defined like in set of time we're using this displacement, so we don't have to worry about these times where we are stopping the driving, and also we can put it in terms of the stress, right, on the upper bound, in the vertical direction. And we define this mark, the duration of the avalanche. We don't take the whole relaxation. We just take the time of the stress drop that coincides more or less with the energy drop, with elastic energy drop, right? These two magnitudes are measured as well. And the kinetic energy, what we measure is the peak of kinetic energy, right? Is the jump here, and I will explain it in a moment why. And then we measure as well the lateral work. Well, this is related as well with the amount of dissipation during the avalanche, right? These are our marks that will define these avalanches, and we will try to find out which are the statistics and what are the measurements that we are interested to compare with what is traditionally measured, let's say, in avalanche models. So considering this elastoplastic theory, right? So when we talk about the avalanche, we usually used to consider a system that has some slippage, and then we consider this velocity profile, usually is arrested, then it jumps and displaces, and this is the avalanche. We consider the size to be like the amount of displacement. This will be a mean field measure, right, that we had over a certain duration. And the energy we measure as something that will be proportional to the kinetic energy that has been released, right? That is with the square of the velocity. And also this is another measurement that can be interesting, is this energy peak. It's like this peak of kinetic energy that is just the maximum value that we observe in this avalanche, right? Now we want to compare this with our simulations, right? And this is we'll spend a little bit of time here just to look how we can manage our data to fit it with these ideas here. So we start just by looking at considering an stability problem, right? And the expected relation that we should observe between the internal elastic energy and the stress drop that we observe in the avalanche, right? So essentially, we would expect that variations of internal elastic energy scales like this, so linearly with the stress drop, right? And considering these terms here, so essentially here I'm normalized by the stress ratio from between the vertical and the lateral ones, and here is just, what we expect to be this internal work, right, that we are performing here. This is the Poisson ratio. Here, these are the elastic, the mechanical elastic constant, right? So essentially what we perform is this approximation that the volume goes like this, considering that these are spherical particles, right, and has the porosity here, and also that these elastic parameters, we can reduce them, so the effective elastic parameter reduces as a function of this density of contact points, right? And we end up with this expression here. So this scales linearly with the n, with the number of particles, and we expect this linear relationship with the strain drop, with the stress drop. Sorry. And then we have this scaling term here that goes with the square of the confining pressure, and this element here that could have some additional dependence on the confining pressure, and this is what we are plotting here. So here I'm trying to find out if there is missing something there, right? So essentially what I see is that this term here essentially goes with confining pressure square a little bit less, 1.91. That means that there could be some minor dependence that I'm losing here, right? And then when we look at the avalanche, so we look at the distribution of avalanches, and we try to normalize all the strain drops by the stress release, right? And we find this linear relation. So we see the linear relation between both, right? We lose something for the small avalanches. This is normal because we have some detection bias, right? Because small avalanches need to be a certain way in order to be detected. But when avalanches are large enough, we recover this linear relationship, and these are these lines here are just a prediction from this scaling. We observe that this is not exactly this confining pressure with a power 2. It's a little bit less what we need to impose here, but again, this probably has to do with this little bit of variation with this term here with confining pressure. Right? And this, what's interesting is that if you consider the elastic energy drop, we see that this linear relation stays here. Of course, when we compare this with dissipation, with the dissipated energy, we see that, okay, for large avalanches, this is more or less the same, but especially here for avalanches at low confining pressures, we see that this doesn't stand. So dissipated energy doesn't scale well with the stress release. And this is important because usually this is what is reported, right, in other systems where you don't have movable lateral walls. So if you are in isostatic conditions, then this will be the same as this, but now we have some work that goes to the lateral walls, right? And this is what causes the difference between that, right? Okay. Now it's interesting to see what happens also to this work, to this lateral work, because I don't know what you will think will happen, but we have two different types of avalanches. We identify some avalanches that are caving in, let's say, the lateral wall. So the lateral wall, so the stress at the lateral walls decreases, so they have to push in to maintain the lateral stress, right? And some other ones that just expand the lateral walls, right? So just increase the span on this direction. This is typical for, so this dominates for low confining pressures, and this dominates, so it means for stiff particles, and this dominates for high confining pressures, it means for soft particles, right? And the interesting thing is that here you see that there is a linear relation between the work and the elastic energy that is released during the avalanche. But here we find a relation that goes with the square of the elastic energy. This is something that we didn't understand. Okay. So regarding the energies, what we take for energies is this measure of the peak of kinetic energy. That you will imagine that this will go with this B2 square, the maximum value of the B2 square, right? But the point is that this in this elastoplastic theory point of view, usually you consider overdamped systems, right? And here we have a lot of inertia. In fact, here very little. I mean, you see the characteristic time of dissipation is much larger than the peak, let's say, of elastic energy, of kinetic energy, and the drop of elastic energy. So we believe that in fact we are in this situation where what we are measuring is actually what it will be the E in elastoplastic theory, and this we can look at this way if you consider that the velocity is proportional to u dot, so the derivative of u of the internal energy, then this energy should be proportional to the integral of this u dot square, and in fact this is what we found, more or less a very good relation between both. So probably what we are saying is that these energy peaks give a good measure of the energy of the sample. Okay. So now looking at the temporal properties of this system. So first of all, what we observe is we look at the inter-event times instead in terms of elastic strain, of the external strain, right? So first thing we observe is that we have an exponential tail for large inter-event times. It means that we are in a situation where more or less avalanches are stationary in time. But also we observe for short times that we have some sort of regularity. So this is not exactly an exponential. This has this drop here on the statistics that we would expect, and this is usually a treatment of some sort of pseudo gap, right, in the residual stresses on the slippage, let's say, right, that you need the residual stresses that you need to activate the next avalanche, right, and this fits well this gamma function here, right. That probably implies that we have this power law distribution of pseudo gaps close to the failure, let's say, to the stress that we are dealing with. We can use this, since we are in finite systems, to try to elucidate the nature of this SES, of this stable evolutionary state. So in terms of this predictability, this is an idea from seismicity, and is that when we are, so suppose that avalanches are triggered at a stability limit, then what will happen is that we drag the avalanche, then we'll have an avalanche of a certain site, and then we will need to load a lot, let's say if this is a long avalanche, we will need to drive it a long time in order to have a new avalanche. So it means that avalanches are time predictable. If you know the size of the previous avalanche, you will know the time to the next one, right? On the contrary, if you consider that this is a kind of a stability basin, right, and then avalanche, the system can progress arbitrarily far away to this stability basin, and then can go back. Then, so it means that the times that it takes to load will be proportional to the size of the next avalanche. Right? This is what is called sleep predictable avalanche or size predictable avalanche. And we compare this with our data. We simply perform here, so looking at the times before and after the avalanche, right, and the sizes before and after the avalanche, and the external stress. And what we observe by looking at the autocorrelation function is that the ones on top are more persistent. This implies that we are closer to a situation where the SES is a stability limit, right? When we get to this SES, then avalanches are triggered, and then we are in a situation of time predictability, right? You can understand it better maybe looking at this distribution between the waiting time and the size of the avalanche before and after that waiting time, and you see that clearly that you have here a linear dependency. I'm showing here all the cloud of points because you see that there is some kind of gap here. So essentially what you observe is this pseudo gap, right? That we seem to observe that we are missing loading times that are smaller than the previous avalanche to this power law here, right? So it means that the SES probably we are closer to a stability limit triggering this avalanche. Okay. So the third part will be on these results that I want to focus. It has to do with the topic of this talk, and is the existence of avalanche criticality and this stable evolution state. Right. So remember this example I showed before, right, with the two examples, the dense and the loose assemblies. Here I'm showing as well where this activity is happening. You see that for the dense assemblies, activity is focused in shear bands, so that this doesn't happen in the loose assemblies. The activity is all around. At the end of the day, it seems doesn't have any kind of effect to the avalanche statistics that we observe, right? So here what I'm showing is with lines and these different dots. With the lines is the distribution of kinetic energies that we observe during the whole this whole interval where the system stays at the SES. And here is the same with elastic energy drop. And you see that both simulations go with the same distribution. They are very similar. And furthermore, you see that here are very different stages of the strain stress curve here, with these marked as A and B, and all of them seems to follow the same distribution. So in essentially, what I'm trying to say is that this is a stationary distribution, right, that doesn't change over time. Once you hit the SES, all avalanches fall within the same distribution, right? We may wonder what happens with this modulus here that is negative and this one that is positive here, how it is possible if the distribution is uniform. So we look at these Pearson coefficients of this effective modulus with the activity rate, the number of avalanche over time. You see that we have some correlations, and also this reload. Let's say that we have the speed of reload that we have on sigma y. We see also a positive correlation and very small correlation with the avalanche size. So actually what is happening here is we have more avalanches than here, right? Not that they are stronger. Okay, so now if we want to study all the simulations together, we find here we have the results of different distributions on internal energy and kinetic energy. And you see that we need to find different ranges if we want to find the exponent here, right, to compare this power loss, right? So the idea is to consider this scaling relationship. So this is a power law with some characteristic forms, with characteristic shape, right? And that this shape has a characteristic scale that goes with some power law exponents. So this essentially for the sizes, this will be the 1.85 that we seen before, and this will be 0.5 that is equivalent to a fractal dimension of 1. It's okay, this, right? So we try to fit this exponent just by plotting the bivariate distribution, so with these averages here, and try to fit them together by writing these new variables, right? And we observe a good fitting within a certain area that is independent, that is not affected by small size effects nor finite size effects. So the resolution limit nor finite size effect, right? We use this to scale our distributions, and then from here we define the range where we are going to measure these exponents by maximum likelihood estimation methods. So we have these three exponents here. This one that describes the relation between k and delta u. We have this one here that is the distribution on u and on k, right? And then if you look at this, we find this relation that, so essentially what we observe is that the only parameter that matters here is this confining pressure, right? Remember, high confining pressure means soft particle, means low rigidity, low confining pressure means high rigidity, right? So here in blue, I'm showing the exponents of the size distribution of these energy drop, these elastic energy drops. And in red, I'm showing the energy distribution, so these kinetic energy peaks, right? This is what we should expect with the mean field theory. We will expect this 1.5 here and this 1.33 here. And you see that for low confining pressure, especially for the red one, that is the one that we have a longer range to integrate over. We see that for low confining pressures, we see a very good agreement with the mean field theory. But as we increase confining pressure, we observe that this goes down to these values of 1 that are closer to what is detected with elastoplastic theory, right? With these models where you consider 2D systems with soft particles, right? And well, I mean, this is like important result that we see a transition depending on the stiffness of the particles of this rigidity. That's what it is that we observe stiff particles, we find mean field solutions. As a particle, we find this elastoplastic theory. And now I just wanted to spend some minutes explaining how we can explain this, at least how we can explain that some non-mean field systems have mean field exponents. And if you were in Andhra Pradesh last week, you know where I'm going on, where I'm going to explain now a little bit. So this is so just to remind about the mean field theory, right? This is a way to introduce it is through the Ising model, with a random field Ising model, right? That is simply considers the Ising Hamiltonian, introducing an internal field to each one of the sites. And the mean field model will be considering that all these interactions, of course, are all-to-all interactions, and we can represent it as a single field. And then, in fact, what I will say the mean field is this H plus M, this contribution, and then every time that we have a flip, we have an increase of 2J over M to this mean field. Okay, so this is a way to represent it. When we have a flip, when we get one of these H values, we will increase by 2J over N the field, right? Then if something else happens, some other field falls within this increase, then this will increase again, etc., right? If we want to study this in integral differential equations, it will be complicated, but we have another tool here, and is to study this as a branching process, right? And this is exactly this kind of mean field behavior is exactly a Poisson branching process. So avalanches grow as a branching process where you have the generation is a measure of time as well. And if you go thermodynamical limit, this mean field avalanches we observe at this Poisson Galton Watson, right? And I'm adding here, this is the exact solution. This is a Borel distribution, right? This is the exact distribution of sizes. And this was reported already by Sechner, but this also was reported by Alex many years ago. I mean, when they were looking at this five-bundle model solution, this is what is called the forward, I think it's the forward rule, let's say the forward propagation rule, right? And it's a little bit hidden, but this is exactly the same result, right? This approximates well with this power law relation with exponent 1.5, right? Sorry, there is a typo here. This will be energies. This distribution of energies on the mean field. This mean field will be this minus 4.3. That is this 1.3. And here is another typo. This should be a 2. This is a minus 2. But we won't look at derivations at all, right? The point is that these exponents here are not exclusive of the Poisson-Galton-Watson. These are common for all memoryless branching processes, right? And what happened now, imagine that instead of having a mean field situation, we have something like this, where the connections, instead of being nearest neighbors, they are random. So this is rewired in a way that is very hard, let's say, to go from this propagating to this spin and then going back to a neighboring spin of this one, for example. What we are doing is to break potential loops that you have when you are restricted to this system, right? So by doing this, the avalanche can grow as a percolation process, and now the cluster size or the avalanche size grows as a tree as well, but more similar to a binomial Carlton-Watson, right? And we still have these the same exponents, very similar exponents, right? And this has been observed in different systems. For example, I mean, in processes where in simulations that seems to break these loops by some way or another, like this works by Peter Rasberger, or this from the group by Ferenc Kuhn. Good. Okay, so what's happening in granular matter? Probably what is happening is something like this. So this is some results, experimental results by the group by late Beringer. And when they observe this is an impact of particles to a granular medium, you see that as you increase the stiffness, these 4 chains that we are looking at, right here, it looks more like an actual network for high stiffness, and for lower stiffness is more smooth, right, and dissipates sooner, let's say, in more ordered way than here. Here it becomes a random network almost, right? So probably this is what is happening in our simulations, is that when we are using considering stiff particles, this, and just remember this, that we observe it here, that the activity, instead of staying in some place, it moves around all the system, right? It can translate and then break potential loops between the dissipation of the avalanche, right? And this is something that can happen as well with porous systems. So this is simulations by using finite element models, right? But introducing these pores, random pores. This is from a group in MIT that they perform these simulations. And you observe that the stress, when they stress the samples, it also focuses your channels through these kind of force networks that are very similar to the ones with porous materials, right? So, and this gives the idea that probably can explain other legacy results that I had. This was working doing my PhD with Eduard Vives. What we did was to compress uniaxially some rocks. In this case, it's not exactly a rock. This is a silica glass that is very taut. It's very fragile, and then what we do is to detect the acoustic noise that it's emerging from these fractures. We report these signals. We integrate this to get the energy, and then to make the statistics of the energy of these signals. And this is, of course, a very porous material as well, right? And what we observe again is this power law distribution of energies with an exponent that is quite close to this mean field, to what's predicted with mean field theory, right? So essentially, this is what we would expect. So this would report a set of 1.5, a little bit higher, but we are very close to these mean field predictions. What happens is that in this case, when we try with different materials that are softer, instead of going down, the exponent goes up. That is something that we don't understand either. But we observe both a dependence on the composition, so in softer particles or tougher particles, and also in the porosity of the particles, right? And this is something that is interesting to see, that this exponent relations, these non-universal exponents in the distribution of energies also happens in these compression experiments with fractures, right? Okay, so that's all. And right on time, good on time? Yeah, okay. I wanted to explain. So first of all, first conclusions is that we try to identify these avalanches by doing this connection with internal measurements, that we find that this elastic energy drops serve as a good measure of sizes, and the kinetic energy peaks have a good measurement of these energies in terms of traditional avalanche dynamics. Then we identify this stable evolutionary state, right? And we see that this behaves not as much as an attractor, but a stability limit, right? Where we observe these SOC avalanches, right? So it seems like it has properties of self-organized criticality, as we expect in this mean field theory as well, when you consider sleep avalanches, right? And but it's not exactly mean field, of course. We've said that this we have these non-universal exponents that matches these mean field models for stiff particles, sorry. And but for soft particles, we obtain these to the exponents expected into these systems, right? Finally, this explanation that I gave about the mean field exponents, that probably is due to the fact that for stiff particles we are closer to a branching process, to a memory branching process, and that may occur due to this structural heterogeneity of this force network, and that we could explain maybe the same. Probably the same explanation for the acoustic emission experiments on fracture as well, right? So for some samples we have mean field theory and some others. So now we are trying to address these different problems. First of all, to understand what's happening with these expanding and contracting avalanches we observe, right? When the walls cave in or expands, depending on the kind of avalanche that we observe. Also, we want to verify whether this transition is smooth or is just sharp and it's just a matter of tiny size effect that we observe at this intermediate stage, right? Shall we go from one universality class to the other, or we have a smooth transition between them, right? Then what we want to look at as well is to determine these avalanche properties at SES. And in terms of these measurements, like anisotropy and fabric anisotropy and coordination number, and outside SES, if we're able to have enough statistics outside the SES to see if we observe a transition toward criticality, right, with these methods, right? And from this, we want to compare as well if we can change, let's say, the potential energy landscape and the kinematics or the inertia of the system. Try to identify secondary effects that have been discussed in the literature. Right? This is just a summary of the bibliography I've shown. Also, I would add that if you want to know more about this idea of the SES, there is a talk by Mehdi Purag, who was the author of this idea, that you can check. Right? It's around the time. This is not the length. This is just the time you have to move. This around 3 hours at the start. Okay, so thank you very much for your attention.
We have time for some questions.
Yeah, nice talk. So 3 things I wanted to ask. So one was about comparison with frictionless systems, because there's a lot of data on frictionless system in the quasi-static limit. And then also for amorphous materials, a lot of data, similar data. I mean, so do you get similar exponents? For example, Salerno Robbins, they're doing it for shear, you are doing for compression. So does the protocol matter? It's because in the later part of the talk, it seems that protocol wouldn't matter, right? And the third would be what you just now mentioned about the kinematics, the dissipation. So you have chosen one model of dissipation in whatever the work that you have done. If you choose underdamped or different kinds of dissipation modes, how the exponents change? Do you have any thoughts?
I don't know. Yeah, I mean, first of all, yeah, of course. I mean, we are comparing at the beginning, right, with frictionless particles, and then, of course, the introduction of friction and elasticity on deformability, it's what breaks this idea of isostasticity, right? I mean, and that's the key, right? That and this is something that, I mean, maybe will be a better person to answer this, but yeah, I mean, that's the idea. I mean, what we are trying to do is to extend these ideas of isostaticity towards the limit of soft matter, right? And in between, we have this area of fragile matter, right? That is the one that is hard to cover, right? And with this different idea, we're trying to approach the problem by different ways. The second question was on the driving, on the driving protocol. Yeah, so notice that the paper is deviatoric stress, right? So that's the idea. I mean, at the end of the day, it doesn't matter that much. At the end of the day, the events that we have are deviatoric. I mean, they're just shear events, right? And it shouldn't matter that much that you compress it or you just shear it, right? Because you have the formation of the shear event.
Robbins would be useful. I mean,
yeah. That's. I mean, in fact, we have, of course, more comparison in the paper, but yeah, I mean, this is the idea, right? For them, they obtain these exponents there that are around this 1.5, right? I think 1.25. Sorry, 1.28, and yeah, I mean, that's the idea. In their case, they were comparing instead of elastic energy drops. So why I showed this with Salerno Robbins is that I mean, they were comparing instead of energy drops dissipation, but it's because it's exactly the same in their case, right? Because they are using constant volume, right? That should be the same. So yes, this is a measure that should be comparable with theirs, right? And the last one is that we need to do more experiments. So, I mean, to play with different parameters, let's say, right? Just to say about different dissipation mechanisms. Of course, we are using, for example, elastic particles, linear elasticity. It shouldn't matter that much, but of course, if you use Hertzian interactions, it could be different. I mean, I don't know.
I have one quick question. So you showed some of these avalanches from energy estimates. Is there some sort of specific events, spatially varying events, like you had a couple of images about the shear localized regions and so on, right? In the first part. So yeah, this one, yes. Yeah. So when you have something that's dense versus loosely packed, how does, like, let's say for some particular loading condition, just tracking back on the previous question of it, if you see, let's say, bunch of bands versus more diffuse deformations, is there something you can say about some of these statistics from that?
So the point is that they seem to be statistically equivalent, right? And we can look at the images. Look, I have here a movie. So this is just the fastest avalanche that is moving. So this is what I represented with these blue dots, right? The fastest and second fastest avalanche bits that are moving during one avalanche, right? And this is a loose assembly. You see that they move. I mean, they can happen everywhere. So a single avalanche can have particles moving all around, right? And you will think that something much different will happen in loose assemblies, in dense assemblies, and it does if you are on this soft particle limit. But on stiff particle, I mean, of course, if they are localized in the shear band, and they are a little bit more focused. But sometimes you have an avalanche that also propagates very far away. So we are still in this situation where, of course, the activity has been focused, but it looks like it's not that important. I mean, on the statistics, what may happen is what happens outside of these bands, right? Probably, I mean, this is something that I'm not an expert, but probably this the assembly is still over compactified there, right? And here we are on the band, we are in the situation where they can sleep, where they can establish this stability limit, right? That is very similar to the one in the loose assembly, right? I guess this is what is happening, but I have no proof of that. Yeah.
And just a thought about, linking back to some of the results we saw in yesterday's talk, if you cycle it, with a certain amplitude and then do a training type readout type of thing, do you expect intuitively different statistics?
I guess, sure. Because especially those what you have, I mean, you have this training. I mean, in loose assemblies, I don't know sure, but in dense assemblies for certain, right? Because you have this localization process. Let's say that the formation of the localization band has to do with this over stiffness, right? With this weakening regime, let's say that we observe. Yeah. So this is definitely like passive deformation, and then if you go back, you'll have some memory on that, right? Certain.